Hi, so this video shows you how to do gap correlation with the data. So this assumes that you've already measured all the boxes and gotten all the data onto the USB stick. Now go to the USB stick and get the data and transfer it over to your hard drive. Okay. Plug the USB stick in your computer, open it up, and then usually I would put them in the folder that I call with the name the plant. So we have the reports folder that contains the CSV file with all the measurements, and you have the folder with all the images. We copy that into a folder that we're doing calibration in here. I've already done it in this case. Next step is to go through the images and find which one is the marked box. What we're going to try to do is to correlate the marked box data and align it up with the data in the spreadsheet. There was the marked box. So I see here the marked box is 31 and 25 millimeter gap measurements. I go in the reports, open up the CSV file that I've downloaded, and I see that here this is the marked box, right? 31 and 25. It's a little harder if you didn't draw the lines, and it then you don't have measurements that are really out of the standard. The next step is to go ahead and create a new spreadsheet where the spreadsheet we would have the caliper measurements, lead gap, trail gap, and the average, the skew. Then we have clear vision, full check, lead gap, trail gap, average, the scaled average, skew. Then we have the error, average error, standard deviation of the error. Now we go into the file where we measured all the boxes, and the marked box was the first box, so I select about 2 bundles worth of data. Then using that data, I put it in the spreadsheet. I generate the average by typing average of lead gap, trail gap, apply that to the whole column, get the skew, which is trail gap minus lead gap, apply that to the whole column. This was the marked box. Now we're going to do the same with the full check data, and we know this is the marked box and that's the first box. And in this case we have roughly 45 boxes. I don't remember the exact number, but we'll just delete the extra. Copy that in. This is the marked box. Same thing, you're going to have the average of lead gap, trail gap. The scaled is just the average times, we're going to start with 1.0, and then we're going to tweak that factor to center the data. And the skew is trail gap minus lead gap. We're going to apply this to the whole column. Then the error is the average caliper minus the average of clear vision, full check. Now don't worry about that number because we know that that first box was bad because it was marked. So we're going to delete that. Here we're going to compute the average of all the errors. And here we're going to compute the standard deviation of all the errors. Now, 0.37 is actually pretty good, but let's look at the data. The next step is to plot out the error. So we're going to insert a scatter plot, and from this plot you can see there's some outliers. Those generally you would go back to your boxes and see if you made errors in measuring. At this point in time, data like this shouldn't happen. It should either be that the FoldCheck algorithms mismeasure the box, and you'll see that on the image, or you can take a look at the box and see maybe you measured it wrong. So I'm going to remove this point because it seems to be an outlier, and this point because it's an outlier. Right. Next step, as we can see here, the data is just a bit out of center. So it seems that our usual data is smaller than what we measured by hand. So I'm going to multiply that by a factor, say 1.05. Apply that to the whole column. Right. And then now we see there's still this point that's a little way off, but we'll accept that. So the data is now a little bit off center still, but in the other direction. So just tweak this factor and see what happens. Now everything seems to be mostly between 0.4 and minus 0.4. So we accept this factor as the factor to multiply the data. So if you want all your numbers to be larger by 2%, that means you want to make the Y resolution to be smaller by 2%. Say the Y res was 2.9, and now you want the Y res to be 2.9 times 1.02. Divide by 1.02, because you want the number to be smaller so that all your measurements are larger. So you use the same factor here that you divide with the factor that you multiplied here. This uses the error plot. And this data is extremely good, 0.25. Generally, if we measure between two humans, you see that the error can be up to 0.2 millimeter standard deviation of the error. So this is nearly as close as two humans measuring. Generally, the results will be between 0.2 and 0.5. And there's some cases where the results are between 0.5 0.7, and above 0.7 I would think that you probably did something wrong in your measurements, and we'll go over those soon enough. Another thing that is interesting to do is to plot the average error versus in FoldCheck versus the average error in the calipers. You can see a cloud of data here, and people like to see the R-square value, but I don't use that number. So we would usually display the R-square value here. 0.86 means that it's fairly well correlated, but it really depends on how much spread of the data you have. Another very interesting curve here is showing the skew. So we can plot the skew of caliper versus the skew of FoldCheck, and you can see in this case in particular, there is some correlation in the skew. So you would say, if I measured 4.5 millimeter skew, your box is probably going to be about 3 millimeters. It won't be zero. It won't be fully corrected like most operators will tell you. Another plot that is very interesting is sometimes you have a standard deviation, the error of 0.8, and then you start wondering, well, what did we do wrong here? Why did that happen? Because that definitely is wrong. So you would go and plot out the average of each, you plot them out as lines. And normally, you'll see that the lines coincide quite a lot. If there was a shift, you'll see that the bumps are a little shifted, and you try to go and shift the data back. It happens, and this is usually human errors rather than a machine error, where you ignore a box, for example. When you were measuring, somebody talked to you and you forgot to measure a box. That'll happen. Or another case that can happen is if you have reversed a bundle, reverse all the boxes in one bundle. Usually you measure two bundles, so if you reverse one bundle and not the other one, you'll see that the correlation on one bundle is much better than the other one. So that's a red flag. Another case we had was we mislabeled the bundle. So bundle number 2 was labeled as 3, and 3 was labeled as 2. So I measured bundle 1 and 2, but it was really 1 and 3. So that didn't coincide and gave us really bad data for the second bundle. At this point in general, if you look at the image, the analysis image, and everything looks fine, with all the red lines on the top gap and the green lines on the bottom gap and the gap measurements here looking correct, most likely it's something wrong with the method or the order in which you measured stuff. So watch out for that. So that shows you how to make the gap correlation file. In general, you would use a template and just fill in these two columns. But we want you to be able to generate these files yourself so that you're able to correct when there's things going wrong with the data.